Welcome to my video course on engineering FRMCS. Today we're tackling one of the absolute coolest parts of modern railway communication. We're talking about the core challenge of routing train data based entirely on how critical that application actually is. When we look at the future railway mobile communication system, FRMCS, running over these massive 5G networks, we're not just, sending simple text messages anymore. We're transmitting just huge amounts of data. And that ranges from the absolutely critical, life-saving safety protocols that can literally stop a moving train, all the way to routine background stuff like time synchronization. So the big question is, how do we guarantee that the critical data gets a dedicated, hyper-secure lane while all that supportive data is still routed efficiently? Well, that's exactly what we're going to master in this explainer.
Here's our agenda for today. First, we'll look at the overarching FRCMS addressing architecture. Second, we're diving into host-to-host routes. Third, host-to-network tunnels. And finally, we'll wrap it all up with an architectural summary. All right, let's jump right in.
Section 1. FRCMS, Addressing Architecture.
Okay, so before we can configure anything at all, we really have to get a grip on how data is conceptualized and routed in a modernized 5G-enabled railway network. Let's lay down some quick foundational terminology so we're all on exactly the same page about what lives in our ecosystem. In the FRMCS addressing scheme, a host is just a single, specific application entity. Think of it like a dedicated solitary endpoint. So if an app needs to talk to just one specific counterpart, it talks to a host. Simple enough, right? On the flip side, a network represents multiple application entities. It's more of a collective domain, basically a whole cloud of resources where several complementary services live together. Trust me, getting this distinction down right now is going to be the absolute key to understanding how we route all our 5G traffic later on.
Moving on to Section 2, Host-to-Host, or H-to-H routes. Now that we have those definitions in our back pocket, let's dive into our first major concept, the host-to-host architecture. This setup is specifically engineered for high-stakes, direct communication, where there is literally zero room for error. If you look at the structure here, on the left, host A represents an application entity right there on board the moving train. Then over on the right, host B is a trackside application entity. Notice how that connection just punches straight from the onboard FRMCS right through the infrastructure and directly to the FRMCS trackside gateway. This H2H principle gives us a completely transparent point-to-point IP connection between those two hosts. It is a direct, dedicated pipeline, nothing in between.
So you're probably asking, when exactly do we actually use this dedicated pipeline? Well, we use it when human lives and massive physical infrastructure are quite literally on the line. This direct host-to-host routing is an absolute non-negotiable mandate for critical, loose-coupled applications. The two big ones here are automatic train protection, or ATP, which covers your European standard systems like ETCS that actively prevent collisions, and automatic train operation, or ATO, which handles the automated driving behavior of the train itself. For these systems, you absolutely cannot have data getting bogged down or delayed by bouncing around a wide web of shared network resources. It needs that ultra-fast, dedicated H-to-H connection. No exceptions.
Let's pop the hood for a second and look at the technical mechanics of how an H2H connection actually spins up. When a session starts, it uses SIP URI formats for destination addresses. You can essentially think of that as a digital phone number. But instead of relying on a hard-coded IP address, which, let's face it, is going to change constantly as a high-speed train blasts across different borders, it uses what we call functional aliases. This is super clever. It means the train basically asks to connect to a specific function, something like, hey, get me the trackside controller for Sector 4, and the system automatically resolves that functional alias into the correct route on the fly. This gives us totally seamless, end-to-end mission-critical data, or MC data IP connectivity, totally regardless of where the train actually is geographically.
And that brilliantly highlights the main divide in our architecture today. H-to-H is purely point-to-point. It is strictly fenced off for those mission-critical applications we just talked about. But as we all know, a modern train needs dozens of other digital services to run securely and accurately. And those background services simply don't need that intense, dedicated pipeline. This brings us to a major shift, moving from point-to-point links over to point-to-cloud networks. And that is the perfect segue into our next architecture.
Section 3. Host-to-network, or H2N tunnels.
All right. Building right off what we just learned, let's explore how we actually build data tunnels for essential but non-critical supportive infrastructure. We do this using the host-to-network addressing scheme.
So we still have our single onboard application host sitting over on the left, but instead of wiring it to a single trackside host, the FRMCS trackside gateway connects it to a publicly reachable domain. Basically, a data network cloud that holds multiple complementary application entities. You can see them labeled here as B, C, and D. In this scenario, the gateway acts like a bridge, seamlessly relaying that data stream toward an IP network where all these partner application entities hang out.
Now, why go through the trouble of this point-to-cloud approach? Well, it's because supportive applications need standard IP addressing over MDS data sessions to do their jobs efficiently. We're talking about workhorse applications here. The domain name system for resolving web addresses, the public key infrastructure, and the key management system for handling all those crucial security certificates. These are the systems constantly running the necessary background checks and balances. Honestly, it would be a total nightmare and incredibly inefficient to try and build dedicated individual point-to-point tunnels for every single one of these background tasks. H2N just bundles all that access together beautifully.
But, as I'm sure you engineers are already thinking, opening up a connection to a much wider data network introduces a massive, glaring security risk. We absolutely cannot have random external servers out on the internet pinging a multi-ton train. So, there is a very strict security mandate hardwired right into the H2N standard. The FRCS trackside gateway acts as an absolute impenetrable firewall here. It explicitly blocks any data network hosts accessed via H2N from originating a session towards the remote onboard host. Think of it this way. The train is totally free to reach out to the network and grab a security key, but the network cannot, under any circumstances, initiate a session down to the train. That one-way initiation rule, it's just a brilliantly simple layer of security.
Section 4. Architectural Summary.
Okay, we have covered a ton of technical ground today. Let's bring both of these concepts together and lock today's academic module into a single, highly practical frame of reference. If you're out there actually configuring one of these systems, here is your ultimate cheat sheet. The host-to-host addressing scheme provides a transparent IP connection between two dedicated hosts. You absolutely must use it for critical applications like automatic train protection and operation. Conversely, the host-to-network addressing scheme connects a single host to a data network. You use that one for complementary, supportive infrastructure, things like DNS and PKI. By strictly enforcing this divide in our traffic, we get the best of all worlds: safety, security, and just massive network efficiency.
Which leaves us with this final thought to chew on. As we look toward the future, toward fully automated, go-for autonomous trains, our networks are going to be pushed to their absolute limits. By rigorously splitting our architectures into H2H and H2N right now, today, how much more efficiently are we going to be able to slice our 5G bandwidth tomorrow? Think about it. How many more advanced automated applications can we safely layer onto a train when we strictly, cleanly separate the mission-critical from the simply supportive? I really want you to take that thought back to your engineering teams as you design the rail networks of the future.
Thanks. We can see you next video.